Okay, so today we're going to continue our discussion with the chemical potential. And this week, we're going to see the equilibrium constant and how it arises from the chemical potential, and our discussion on how to formulate spontaneity of processes under certain experimental conditions. And then what happens at equilibrium, or when the system reaches a stable state. Okay, so at the end of last class, we ended up looking at the chemical potential of a single component, and in particular, a fluid that is modeled by the ideal gas equation of state. And we saw that we could write the total differential of the chemical potential for a single species, pure species, in this form. Okay, where we have the total differential of the chemical potential, in this case of an ideal gas, that's equal to RT dP over P, and this is at constant temperature. And this arises from the fact that for a single component, d mu is given by V bar times dP minus S bar times dt, where the bars indicate molar properties. And this expression, of course, came from the fact that we have two ways to represent the total differential of G. The first is our combination of first and second laws, okay, which we saw last class, which is given by this expression. And then we also saw that, well, I told you that we can write G as the sum over all species in a system, the product over all species of mu sub I times n sub I. So the chemical potential of a species I times the number of moles of that species present in the system. So when we use this guy to take the total differential of G, we get a different expression. We can equate the two expressions that we get, and we come up with this expression in the box. And for a single component where m is equal to n, 1, we see that this reduces to this guy, and then we can pose this into molar properties just by dividing through by the number of moles of n, the species we have. Oops, okay, we don't want that. Okay, so let's continue today. We can use that expression, and we saw for the ideal gas that we have this expression. So let me just rewrite it. Mu ideal gas at a particular temperature and pressure is equal to mu ideal gas at a particular temperature and reference pressure, P sub 0, a superscript of 0, usually taken to be 1 bar, plus RT natural log P over P naught. And so what this is saying is that the chemical potential at a particular combination of temperature and pressure for a pure species of ideal gas, okay, so the chemical potential, which is really for a pure species just a molar Gibbs free energy at a particular temperature and pressure, is equal to the chemical potential of that fluid or that substance at the temperature that we are interested in, but at a pressure of P superscript 0, which is often 1 bar, okay, plus a contribution that comes from RT natural log of the ratio of P over P0, okay? And what I want you to keep in mind is that in the log, we have a ratio of P over P0, okay? And we have to keep that in mind because you can't take logs of things with dimensions. So oftentimes what you'll see is mu ideal gas at a particular temperature and pressure is equal to mu ideal gas plus RT natural log of P, okay? And for those of you who are inclined to look at details of things, this is not quite consistent unless you're told that P sub 0 is equal to 1 bar. And in fact, what you're doing here is taking into account that there's a ratio of P over P superscript 0, and that P superscript 0 is 1 bar. But oftentimes you'll see this expression, okay? And somewhere in the text that accompanies it is this qualifier that P sub 0 is equal to 1 bar, and so you have this log of P. but you have to keep in mind that you can't take the log, natural log or log base 10 or log anything of something with units, because that doesn't make sense. And so if you keep this in mind all the time, rather than these things that are just given to you, everything would be much more clear. Okay, so this is what I'm going to keep using, and I will keep reiterating the fact that there's a p superscript 0 as a reference state. Okay. All right, so let's go on now, and we'll use this expression now to look at a particular problem or example. And here we want to look at the chemical potential of an ideal gas in a mixture of ideal gases. Okay. And so now we're going to make use of a lot of the concepts that we've run across in the last couple of weeks. Okay. And so now we're putting things together for very useful things. And so let's take a look at the system we have here. So let's just think about this, right? So we have a container at a particular temperature and pressure. And so we have gas A, and then in another color, we could have gas, let me make those X's, gas B. It doesn't matter which is A and which is B, okay? So B is equal to an ideal gas, and A is an ideal gas. So you have two ideal gases, okay, in the system. And what we want to ask is, equivalently, we can pose this in terms of A, but the same thing applies for B. Okay, and if we had more than two gases, the result is going to apply to each and every one of the species in the mixture. Okay, the question is, what is mu sub A at a particular temperature and pressure that corresponds to the mixture? So the mixture is at temperature T and pressure P. Okay, so we want to know then, what is the chemical potential of A at the temperature T, at the pressure P? And I can sort of qualify this a little bit further. We're going to have N sub I, meaning that we have Na and Nb. So we're going to have N moles of A and N moles of B. Okay, everyone clear with the setup of the question and the experiment that we're going to, well, I haven't said the experiment yet, but. Okay, so let's continue. So the way we're going to do this, again, temperature is constant, okay? And we're going to set up this system here, okay? In order to answer this question, okay, we're going to set up a system or some experimental box or whatever you call it, whatever you want to call it. And the way we're going to do this is, let's see, on the left-hand side, we're going to have A and B as our mixture. So this is our ideal gas mixture. Okay, there's going to be a temperature T, and there's going to be a pressure P, and that P is going to be P total, because we know from all of our courses and perhaps even high school that in a mixture of ideal gases, P total, because they're ideal, is just equal to the partial pressure of A plus the partial pressure of B. And in the system of this mixture, A does not see B and B does not see A. That's the whole point of an ideal gas, right? They don't see one another. And so it's, for all intents and purposes, it's the most ideal case in that the total pressure is just the sum of the two pressures. So, if you think about pressure as collisions, the force imparted on a wall based on collisions, well, if you have two types of ideal gases, then the total force on average is the force that the A particles and the force that the B particles exert. Okay, so that's where we get this notion of P total is equal to PA plus PB for an ideal gas mixture. It all arises from the fact that A does not see B. Okay, only the wall sees A and B. But the wall doesn't care what A and B are. They're just particles hitting the wall. Okay, so that's why it's additive. This is called an additive model, very simple model. Okay, so keep this in mind, but you should already know this for an ideal gas. So P total on this side is P, and that's equal to the partial pressure of A plus the partial pressure of B, okay? And we actually know that the partial pressure of A is going to be Y sub A, which is the mole fraction of A times P total. And the partial pressure of B is the mole fraction of B times P total. Again, this is just because they're ideal gas, okay? And we know that YA plus YB is equal to 1, okay? And in fact, if we have M components, that would just be Y sub I is equal to 1 to M, and that is going to have to equal 1. All the mole fractions have to add up to 1. That's obvious, I think. Okay, so that's the setup and some important equations that we need to keep in mind. Now in the system, let's go back to that. What we're going to have separating the left-hand side from the right-hand side is a semi-permeable membrane. Semi-permeable membrane, and this membrane is only permeable to A. We're going to just say it's only permeable to A. That means B is blocked. So A can go over all the volume that's included in both sides of this container. B is only left on the left-hand side because this membrane is not permeable to B. Okay. And so on this side we have A, and it's going to be pure. Okay. And this is a single ideal gas on this side because it's only A. The temperature is going to be T. And on this side, we're going to have some pressure, and we can just let that pressure be P sub A. Okay. It's going to have to be P sub A. All right. Any questions so far about the semi-permeable membrane? Okay. So I want to ask right now that there's a partial, does everyone understand that there's a partial pressure of A on the left-hand side and why that has to be? Okay. I hope everyone understands why, right? There's a partial pressure. So that the gas A on the left-hand part of this container is going to exert a partial pressure, which is force per unit area of P sub A on the walls. Okay. Now, is that going to be the same as this P sub A that I've written on the right-hand side of the membrane? Is that going to be the same? So are the two P's, so I had P sub A here, right? For the left-hand side as the partial pressure of A. Is that P sub A going to be equal to this P sub A? And I welcome any responses. Yes or no?
I don't think it will be.
Why?
Because isn't there some A still left on the left side? So not all of A is on the right, making it equal to that total pressure, just A.
Right. No, you're right. There is A on both sides. A is, so A essentially, this, let me sort of, so does, for all intents and purposes, does A see the membrane? Is that membrane of any consequence to the gas A?
No, because it can go back and forth through both sides, correct?
Exactly.
So it would be the same.
Okay, good. All right. So, okay, that's right. It's the same. It has to be, okay, because you have this permeable membrane. So A can essentially go through it. And so for A, there is no membrane. And so if you have a partial pressure A on the left-hand side, because there's a mixture, then the pressure exerted by A has to be the same on the other, it has to be equal to that on the other side, because essentially there can't be a gradient in pressure in this system at equilibrium. So for the, I'm sorry, I don't have my names up, but for the first student who responded, does that make sense to you now?
Yeah, that makes sense.
Okay. Who was that, by the way?
Alex.
Alex, okay, yeah, so thanks, Alex. Yeah, thanks for the response, but, and I think Michael was the second student. That's, okay, so you both, thanks for the contribution to the discussion. Okay, so the piece of A in this case is, for A is the same on both sides. And the easy way to think about that is, for A, there is no membrane. Just think about A not seeing the membrane at all. And so it's distributed, and it doesn't see B. So A doesn't see the membrane, and A doesn't see B because they're ideal. So for all intents and purposes, A is moving freely all through the whole container. And so it has to have one pressure when the system is at equilibrium. Okay, so the nomenclature I've used, right, is to indicate that this piece of A is going to be the same on both sides. Okay, so that's great because we have pure A on the right-hand side, okay? And that's good because we know how to compute the chemical potential of a pure species, and in fact, a pure ideal gas at a particular temperature and a particular pressure. We just saw that right here. We know how to do that. Okay, so let's see what we can get, or where we can get with this. So we know on the right-hand side, that's right-hand side, okay? Mu sub A, which is at temperature T and P sub A, is going to be mu sub A. And since this is all at constant temperature, we're just going to let that be P sub A superscript 0. We'll have some reference pressure. We can let it be 1 bar, but for the purposes of generality at the moment, we'll just say that that mu sub A is at T and P sub A is equal to mu sub A at T and P A superscript 0 plus RT natural log P of A over P of A superscript 0. And this expression is just this expression right here in the box. Okay, that's all it is. With a subscript A now for everything. Okay, and A is an ideal gas. All right, so that's what we have. So let's see. What do we know about chemical potentials from our last discussion? So it seems that we know what, so let me reiterate here just to get everyone on the same page. A doesn't see the membrane because the membrane is permeable. So A sees the whole volume of this container, and A doesn't see B. Okay, so for all intents and purposes, A is living the good life by itself in this container. Okay, and so we said that on the right-hand side, the chemical potential of A, we just computed that, is T P sub A. So what do you think the chemical potential of A must be on the left-hand side? Sorry? Oh, okay, I thought somebody responded. So if we say that this volume, this container, is our total system, and we break it down into two subsystems, right? One subsystem, if you recall from last lecture, is this capital 1, and we could say that's the right-hand side. And the other subsystem is capital II, and we can say that's the left-hand side. And if the system is at equilibrium, what can we say about the chemical potential of A?
Should be the same on both sides.
Exactly, it has to be the same on both sides. Okay, so what that means is, right, that's why that result was such an important result about the chemical potential, that mu A on the right-hand side at T and PA must equal mu A on the left-hand side at T and, of course, P total. Okay, we have a total pressure now, which is the partial pressure of A and the partial pressure, and actually of B. And let me actually make this a little bit more clear. Okay, let me make it a little bit more clear so that you can, when you go back. So on the right-hand side, we have T partial pressure of A, and we have pure A. And on the right and on the left-hand side, we have mixture. Okay, just to make sure. But of course, we know that since A doesn't see anything in the system, the two A's, the chemical potential of the two A's has to be the same. All right, any questions on that or comments?
Actually, quick question. What do RHS and CHS stand for?
Well, this is left-hand side and right-hand side
Okay.
of the box. So on the left-hand side, I have a mixture, and on the right-hand side, I have the pure. A, species A. Okay? So let's see. So, and this is what we want, okay? But we know this guy because we just computed right here what that guy is. Okay? So let's just substitute that in. Remember, the question we were after was, what is mu sub A in the mixture? What is mu sub A in the mixture? Okay, and so let me put mu sub A now at T P total, which is in the mixture on the left-hand side. And that's equal to mu sub A, which is T P A, and this is pure. Okay. And we know what the pure is. It's right here. Okay, I'm going to put that in here now. That's equal to mu A T P A naught plus RT natural log PA over PA naught. And that's equal to the chemical potential of A T at P total, which is the total pressure of the mixture. Okay. And this is because the chemical potential of A has to be the same on both sides. We're not done yet. We're going to massage this equation a little bit more to give us a little bit more insight. But this is this intermediate step, and it's based on the fact that we know what the chemical potential of a pure ideal gas is. Okay, that's one. And we also know that in a system, if we subdivide the system arbitrarily into subsystems, at equilibrium, the chemical potential of that species has to be the same throughout the system. So those two very important conceptual elements go into this expression here. Okay. So now we know that P sub A, this guy, P sub A, right, which is, if you want to call it the pressure of A on the right-hand side, has to equal the pressure of A on the left-hand side. So the pressure of A on the left-hand side is just the partial pressure of A. Okay. The P sub A on the left-hand side is just the partial pressure of A. So we know that PA is equal to YA, which is the mole fraction of A times P total. Okay, that's this thing right here. So it's YA times P total, because we know that the two P sub A's on the right and on the left are equal. And we know on the left, P sub A is equal to Y sub A times P total. So we're going to use that result. So we're going to write mu sub A at T P total in the mixture of ideal gases is equal to mu sub A T P A naught plus RT natural log. And now P sub A is equal to Y sub A times P total over P sub A naught. Okay, I'm going to stop here. Everyone is on board with this last expression I wrote or not? If there's any need for discussion, I will entertain. Okay, let's continue then. So now we can decompose or decouple elements of that log, the argument of the log, because we have products there. So, you know, when you have products in the argument of a log, you can make that into a sum. So that's what we're going to do. Okay, so what we have here is this mu A at T PA superscript 0 plus RT natural log. What I'm going to do here is I'm going to isolate the Y sub A term. Okay, and so what I'm going to be left with is P total over PA superscript 0 plus RT natural log of y sub a. So what I did here was to say that in the natural log in this equation, I have the product of y sub a times the ratio of p total over pa superscript 0. Okay. And since I have a product, all I did was decompose the log into the sum, because log of a times b is equal to log of a plus log of b. That gives me this expression. Okay. So now what I can say, and it's very cool, is that this guy, right, is the same thing as taking A from pressure PA superscript 0 to pressure P total, right? It's the same thing. That's what we use. That's this equation right here, right? It's the same thing. Mu A starting at T and PA superscript 0. Well, that's where it's starting, T and PA superscript 0. And now it's ending up at not P sub A, but P total right here. So what I can do is just rewrite this guy as mu A at temperature P total, okay, plus RT natural log y sub A. And so this is the chemical potential of A in the mixture. That's equal to mu A T P total. And I should point out that this is for the pure A plus RT natural log y sub A. And this is the result that we get for the chemical potential of a particular species I in an ideal gas mixture when the mole fraction of that species in that mixture is y sub A. And let me just say that y sub A is equal to n sub A over n total. Okay, and in this case, since we only have two, it's n A plus nb. That's what n total is equal to. So okay, any questions so far or any comments? So this is the big punchline so far, very important punchline. Very important. So if there's any need for discussion, I'm my pleasure to discuss. No? Okay. Okay. So let's look at this equation and see what it's telling us. Okay. So this expression is telling us that what the chemical potential of A is in a mixture of ideal gases. But if you look a little bit carefully here, we see that that chemical potential is composed of one part, which is the chemical potential of A, as though it were pure at the same conditions of temperature and pressure as the mixture. Okay, so we have two contributions to the chemical potential of A in the mixture. The first contribution is the chemical potential of A as though it were pure, but at the same temperature and total pressure as the mixture. Okay, and that's what this first term is. Okay, so this is pure A at T and P total, where that P total is the total pressure of the mixture. Okay, plus this contribution from this mole fraction, or the fact that there's a mixture here. Okay, and so this then is going to be due to the fact, due to mixing. Okay. So what is the log of something? So let's put it this way. What is the range of values that y sub A can take in the mixture? So y sub A can be less than or equal to, well, it can't be equal because there's a mixture. So it can be between 0 and 1, right? And if you have a mixture, then it can't be 0 or 1, but it can be anything in between. And so the natural log of y sub A, sorry, natural log y sub A, what's going to be the sign, SIGN? Anyone want to hazard a guess?
Negative.
Negative, exactly. Because the log of something that's less than 1 is negative. And so this term, the term due to mixing, is going to reduce the chemical potential of A from its pure value at the temperature and P total in which you find that mixture, and it's going to lower the chemical potential of A in the mixture. So therefore, thus, because of mixing, mu sub A is lowered in a mixture. Okay, so mixing lowers the chemical potential. Mixing lowers the chemical potential, okay, of all species. And so therefore, for all species in a mixture of ideal gases, mu sub I at T P total, and now I'm going to just say we have Y sub I, okay, is going to be equal to mu sub I at T P total pure plus RT natural log Y sub I. Okay, because Y sub I is going to be less than 1, that's going to contribute to a lowering of the chemical potential. Any questions on that? And that's profound result, because when we mix things, the chemical potentials of all of the species relative to their pure state are going to be lowered. Okay. And where have we seen this like RT mole fraction kind of form? So note, we have seen a form, the form of RT natural log of a mole fraction. Or we could say RT natural log XI somewhere before. Where did we see that? Do you remember?
Is it entropy, the probabilistic view?
Okay, and that's exactly right. And do you remember what thermodynamic potential we were computing changes in when we saw this RT log XI kind of a form?
I think it was W microstates, or
Okay.
maybe that was in the argument of the LN.
Okay, so now let's go back to something more, but when I say thermodynamic potential, I'm talking about something like G, U, H. So those are thermodynamic potentials. So do you remember what we were computing delta for when we saw that? You're right. So what is the microstate, what that whole concept of microstates and probability, what is it related to?
Was it delta H?
No. Microstates. What is central to what thermodynamic entity are microstates important for?
For entropy?
Yeah, exactly. So remember, we saw that delta S mixing of ideal gases is equal to NR, the sum of XI natural log XI, this product, where we have a sum over I equals 1 to M if you have M species. And in this case, if we have 2, it's just NR, where N is the total number of moles. You would have XA natural log XA plus XB natural log XB. Remember? And so we see that the chemical potential lowering, this free energy lowering, in the mixture is arising from something that is related to entropy. So the entropy of mixing is what's causing this lowering of the chemical potential. Now, if we think about this, remember the chemical potential of a pure species is really G of A divided by N of A, right? But it's really this molar Gibbs free energy. Molar Gibbs free energy, right? And we know that G is equal to H minus TS. So therefore, delta G is equal to delta H minus delta TS. Okay, and at constant temperature, that would just be delta H minus T delta S. Okay, T is equal to constant. But in an ideal gas, what is H? Is there any H for an ideal gas, more or less?
At constant T, since dt would be 0, I suppose H would be 0.
Delta H would be 0. Okay, good. Okay, that's one way. That's exactly right. So we know that for ideal gases, H is a function of temperature. And so actually, I should say, right, this is for mixing. My apologies. This is for mixing. So what would delta H mixing be for ideal gases? It would be at constant temperature, it would just be zero. And so we see here that the delta G of mixing is totally driven by the entropy of mixing. And this is reflected now in the fact that our chemical potentials for each of the species are reduced from their pure state by contribution that's log of x sub I or y sub I, these mole fractions. Okay. Any questions? Okay, no questions. All right. All right. So let's keep that in mind. So we have this expression now and this expression right here. Okay, so and we have several, but now we're going to use. So we have this guy, and this guy. We have three expressions we could use to give us the chemical potential of A in a mixture. Any questions? I want to make sure everyone's got that. Okay, okay. Final note. We know mu sub A in the mixture. We know mu sub B now in very general terms because we could just, in all of these equations, we replace A by B. So we have TP total mixture. So G in the mixture at TP total is just going to be equal to mu sub A times N sub A plus mu sub B times N sub B, where mu sub A is just mu sub A at a temperature P total pure plus RT natural log Y sub A. And we have the same thing for B plus mu sub B at TP total pure plus RT natural log Y sub B. Okay, so those are the two chemical potentials. Right, and that's G for the mixture. Any questions on that? Okay, and I just want you to keep in mind that we can also write the chemical potential of A in terms of the partial pressure right here. Right, so we could write this as mu sub A at the temperature T and reference pressure that we choose, plus RT natural log of the ratio of the partial pressure of A in the mixture divided by the pressure that we choose as our reference. Questions, comments? Seriously. Okay, last time. Any questions, comments? Okay. Right, write this down. We're going to use this. We're going to use this form. We're going to use this form for a little while now. Okay, so write that down. But all the forms that I've shown are equivalent. You should be able to move from one to the other rather easily. Okay, and it's just algebra. There's nothing difficult here at all. Because now what we want to do, or I want to do, is look at something that I know you've all been waiting for. Right? I know you've all been holding your breath for this. So now we're going to look at chemical equilibrium. Okay. Now we're going to see some things that you've seen in Gen Chem, but now we're going to go through a different way. So chemical equilibrium, I'm going to put this in a very general form. We're going to use a very general expression, a chemical equation. We're going to have our stoichiometric coefficients, nu sub A with chemical species A, plus the stoichiometric coefficient nu sub B for chemical species B. And we're going to say that we have reversibility, a reversible chemical reaction at equilibrium, this dynamic equilibrium. And we're going to have products nu sub C times species C plus nu sub D times species D. Okay, well, this is a very general abstract chemical equation, or we can call it a chemical transformation. And a transformation is a process, right? So this is, again, just another way of writing a process. And process is something that everyone can understand. A chemical equation is something that perhaps only chemists can understand. So if we think about this in a broad way, it helps us understand things in a much more useful and practical way. So we're going to say that we have ideal gases. All of these guys are ideal gases. That's pretty cool because we've developed some tools, mathematical machinery to look at ideal gases. Okay. And we're going to say that this chemical process, this transformation, occurs at temperature and pressure constant. So our chemical transformation process occurs at pressure equals constant. So it's some pressure, I don't know what it is some constant, and T is equal to a constant value. Okay. So, and this is a reversible chemical reaction. So let me ask you this. At equilibrium, right, since we're dealing with equilibrium in this course, at equilibrium, how many species would you observe in your vessel, your reaction vessel? As a chemist, let's say you start with, in scenario one, if you start with species A and B, right, in a sufficiently stoichiometric amounts that a transformation can occur. Okay, you know about limiting reactants and all that. So let's just say we don't have to worry about that, right? And so if you start with A and B in your reaction vessel of interest, what is going to happen at equilibrium? What would you see at equilibrium? How many species, and what would they be in this container at equilibrium?
You would see 4 species.
Okay, Khalil, and which 4?
You said it was A and B.
Initially to start out with.
So you'd have some at A left, some at B left, and then I guess the 2 products it made. So I guess C and D.
Exactly. Good. That's exactly right. You would have A, B, C, and D at chemical equilibrium. Even if you started with A and B, right? Because this thing is reversible, this process, and it's at equilibrium, you would have A, B, C, and D. Okay. Everyone got that? So what that means is, All right. If I define this abstract thing, and don't be afraid of abstraction, you should actually be, abstraction should be your friend, not your enemy. I'm going to label something called epsilon, and I'm going to let that be the extent of complete transformation. Or in other words, I'm going to let that be extent of reaction. If we're chemists, if we're only talking amongst chemists, we'll call that extent of reaction. But if you want to look at this as a very general thing, we'll let epsilon be the extent of complete transformation. And by complete transformation, what I mean is I start with something on the left, A and B. And if it's a complete transformation, I have no longer A and B, I only have C and D. If that were a complete transformation. But we're talking about a process here in which at equilibrium, as indicated by these arrows going both left and right, that we have A, B, C, and D at equilibrium. As Khalil said correctly, that we would have all 4 species at equilibrium. Okay, so the extent of reaction, this epsilon, which can take on values between 0 and 1, okay, at chemical equilibrium, what might you say about the value of epsilon? Can you make any statement or comment about that? Just based on logic.
Would it be 1/2?
Why 1/2?
The reaction's happening, so it's not 0, and it's not happening completely 1, so it'd be happening equally one way than the other.
Ah, okay. Great response. What I'm going to say here is that, thank you for the segue here. We don't know what it is. We don't know if it's 1/2. You're right. You're totally right, Chris, that it's not 0 and it's not 1 because it's at equilibrium. And the discussion, this great discussion so far has made it clear that we're going to have all 4 of species present. So epsilon, this extent of the transformation, how much of that complete transformation has occurred, it's not going to be 0 and it's not going to be 1, but we don't know if it's 1/2 yet. So that is the central question. Thanks for the segue. That is the central question that we want to answer now, right, with all of the thermodynamic machinery that we've developed so far. So let me sort of write this down in this way. Is a graph. Here's epsilon, our extent of complete transformation. And as we've said, that it can be from 0 and 1, okay? But we don't know where. We don't know what value that epsilon is going to be. It could be 1/2, certainly, okay? But we don't know where. So what I'm going to write here on the y-axis is G, our Gibbs free energy. And I'm going to use G because I said, oh, I'm going to let T and P be constant. It's something that I'm going to control, right? Those are the knobs I can turn. So for this reaction, I'm going to control the knobs of temperature and pressure, and I'm going to see what happens at these conditions. So I'm going to deal with G because that's the appropriate thermodynamic potential. So I'm going to plot on this this axis, G of the temperature, the pressure that we are interested in. And it'll, of course, be a function of the moles I have of all of the species. And it's going to be a function of epsilon. Okay. It's going to have to be a function of epsilon. And what we'll find is that somewhere, G will start off here when we have just the components A and B. Okay. And it'll probably end up somewhere else here if we had no A or B. It could be higher or it could be lower. But somewhere along that path, somewhere, we don't know where yet, G is going to do something like this. And what we'll find is that G is going to be a minimum. Okay, G is going to be a minimum. So if we start with A and B, okay, we see that the system is not a stable equilibrium state according to this prescription, i.e. the chemical equation that we've been given. So according to this prescription, we know that A and B alone under the conditions of temperature and pressure of interest is not a stable equilibrium system. So something is going to happen under conditions of T and P constant. And what's going to happen is G is going to be lowered. Okay. And we know G is a function of temperature, pressure, but also of all the moles in the system and their chemical potentials and the extent of reaction now. What happens is that G is going to be minimized. Remember, dG is less than 0 for spontaneous processes under conditions of temperature, pressure constant. It's going to be minimized at some particular value, epsilon star. It's going to be minimized there. And that epsilon star is going to be your equilibrium extent of reaction or extent of complete transformation. And that's what we want to find using our thermodynamic tools. Now, remember when you did in Gen Chem or earlier courses, remember when you had these ice problems and you would say, all right, well, you know, I have maybe used X or maybe you used Y. I don't know what variables you use, but you say, all right, initially I had this amount, how much reacted, and you let it be X. And then final amount, you know, you would use the stoichiometry and you would fill in everything. If X amount of whatever particular species reacted, you know, you would fill it out. In this case, the analog of that X is this epsilon, okay? And that X, you don't know what it is a priori. You have to figure that out, and we'll figure that out. And that epsilon, and that point where G is minimized is related to the equilibrium constant. Okay, that equilibrium constant tells you which way or which side of those two double arrows the equilibrium is balanced. Okay, will you have more A and B or more C and D? Okay, if it's 1/2, if epsilon is 1/2, they will be roughly in the same proportions. Okay, so that is our next goal. Okay, we're going to use our tools now to find where this G is minimized and the equilibrium constant for ideal gas chemical reactions at constant temperature and pressure. All right, thank you all for a great discussion today. I wish you a great week. Any questions before I end the meeting? Okay. Well then, be well, be safe, and enjoy the great sun and outdoors. Okay.
Thank you.
Take care.
Have a nice day.
Thank you too. You too, everyone.